Okay, so after the activity in class, you should have a beginning of an idea of velocity and waves. And we'll just use this as some more practice. So, waves have velocities, okay? They move through space at a certain amount of speed, meters per second. One thing that is going to be important to us in this class is that for light, velocity has a constant speed, okay, of 3.0 times 10 to the 8th meters per second. But we'll get to that in a moment. Okay? This relationship was shown to you in the activity, but velocity of a wave is always equal to its frequency times its wavelength. Okay? You can also think of this as velocity equals wavelength over period. Why am I able to make that adjustment? If I replace frequency with 1 over period, that's what the equation looks like. Okay? So you can use either variation. The one that I have boxed here, though, is going to be the one that I give you on tests and quizzes. So just a couple of basic wave problems, just to also get some more practice with identifying frequencies and things. So what is the velocity of a wave with a wavelength of 3 meters, and it completes 5 waves every second? Okay, this part right here should communicate to you frequency. It's 5 waves per second, or 5 hertz. Okay, and then our length is the 3 meters. So if we use SU, we have velocity equals wavelength times frequency. Velocity is going to equal 5 times 3, and that's going to be hertz times meters, and that's going to become 15 hertz meters, or you can rearrange that just a little bit and do meters times 1 over seconds, which is going to become 15 meters per second. Okay? Just so you can see those units work out. Another very similar problem says, what is the velocity of a wave with a wavelength of 3 meters, and it completes 1 wavelength in 5 seconds? Okay, so this is one where this is communicating you how much 1 wavelength is, so that's your period. Your period is 5 seconds. Okay, so a couple things you can go here. You can use the velocity equals wavelength over period, or you can go and flip this into 1 over 5, which equals 0.2 hertz. Either way works. So again, go to our equation. Velocity equals frequency times wavelength. If I substitute in, I'm going to have velocity equals 0.2 hertz times 3 meters. And that's going to give me velocity equals 0.6. Then I can think of this as meter hertz, or meters times 1 over a second, which will give me the 0.6 meters per second. That makes sense for velocity. Okay? Simple, basic approach to this. Now, in terms of chemistry and electrons, light is the wave that we will deal most frequently with. Okay? If something gives off light, it's either reacting or giving off energy. Okay? So a lot of times in chemistry, the presence of light can allow us to calculate certain things. So the equation, when you're dealing with light, looks very similar, except we just replace velocity with c. And c stands for that constant speed that light always has, 3.0 times 10 to the 8th meters per second. Okay? So that number is what c represents. Okay? So we'll talk about the electromagnetic spectrum some more, but light spans a wide range of different waves. There are some everything on here, number-wise, is related to wavelength. So there are light waves that have wavelengths of 10 to the 4th meters, so 10,000, in the tens of thousands. There's also things that, such as gamma rays, which are 10 to the negative 14th meters. Now, within this electromagnetic spectrum of light waves, there's this little range right here that we can actually see. Okay? And that comes into our eyes, and our eyes can actually take those wavelengths and turn them into something that our brains understand as colors. Alright? So, let's talk about this visible light range some more. So, again, just repeat, only a small portion of actual light waves can be seen by our eyes. Alright? And the eyes perceive those colors based on the frequency or wavelength of the wave, and then that gets transmitted to our brains, and we understand pink is pink or blue is blue. Alright? So, the rainbow colors that we see, or the colors that wavelengths have, come from the rainbow. They go from, if we are talking longest to shortest, Roy G. Biv. That's the thing I was taught when I was a kid to remember the different colors. Red, orange, yellow, green, blue, indigo, violet. Indigo and blue kind of fall into the same category, but just so that you have something to help you remember. And then you're going to notice lengths related to this unit, nanometer. Okay, a nanometer is 10 to the negative 9th meters. So very, 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 very tiny length here. Okay? And when using nanometers, visible light range falls in the hundreds of nanometers, this 700 to 390 nanometer range. Another thing you may see is an angstrom. That is another commonly used unit when dealing with visible light. An angstrom is 10 to the negative 10th meters. So if you see colors in angstroms, they're going to go from 7,000 to 3,900 angstrom. Okay? So, let's apply these numbers to some problems. Because one of the most important things you're going to have to be able to do is calculate wavelengths and frequencies from the other piece. So, for example, red light is 700 nanometers. What if you needed to know the frequency? Okay, your equation is going to be your C equals frequency times wavelength. Or if you rearrange that, frequency is going to be the speed of light over the wavelength. So that's going to be 3.0 times 10 to the 8th meters per second divided by 700 nanometers. But is that going to work as far as our units go? Well, nanometers cancel out meters. So in this case, you're going to do 700 times 10 to the negative 9th meters. Okay? If you plug that into a calculator, you get 0.286 times 10 to the 14th meters per second over meters. Your meters cancel out, leaving you with 1 over seconds, which does turn this into 4.286 times 10 to the 14th hertz. Okay? These are going to be some pretty simple equations, but when we get into applying it to electrons, some of the conceptual stuff will get a little more complicated. So, one more practice one. I say pause the video, see if you can do it out on your own first. But calculate the wavelength of this wave and then determine if it falls within that range of what we can see. So if I were to do this, I have speed of light is equal to frequency times wavelength. Wavelength is going to be equal to the speed of light over frequency. Plug things in, and wavelength is equal to 3.0 times 10 to the 8th meters per second, divided by 7.8, 10 to the 35th hertz, which will give you 3.84, let's stop at 8 because of sig figs, 3.8 times 10 to the negative 28th. And then if you pay attention to your units, you have meters per second over 1 over a second. The 1 over seconds cancel out, leaving you with 3.8 times 10 to the negative 28 meters. So looking at that number, 3 times 10 to the negative 28th, we're not dealing with hundreds to the negative 9th or thousands to the negative 10th. This is not a visible wave. Okay? So make sure you have notes for in class. Don't forget about the email over the weekend, and see you on Monday.